Ciao, buongiorno. Buongiorno.
Buongiorno.
Buongiorno. Come va? Okay. So I'm glad this cooperation has worked through different classes of variables, from operational risk to wars to this. And but I would like to thank particularly Benoit, the late Benoit Ben Melbrot, because it was really his idea that we have very fat-tailed variables, and one of them would be pandemics, of course. And I remember a conversation with him, a long conversation. He could spot fat-tailed variables where you and I can't see them. I mean, at the time, okay, maybe we're learning. Maybe one day we'll be half as good as he was.
Yeah, hopefully, yes.
Hopefully, that'd be enough for me. Third, what at the 10th is good. Okay, anyway. So the idea that we're doing here is to say that you should study properties of random variables rather than just issue forecasts, ideally forecasts, because if you have all this, a forecast is meaningless. And also because we don't produce decisions based on forecasts, but we make our decisions based on total risk for society.
Indeed.
Things like that. So you need to understand the tail properties. And our inspiration has been, for a long time, the models used in hydrology by the Dutch. I mean, this is how extreme value theory has started. And this is sort of our intellectual habitat. Wouldn't you say so, Pasquale?
Yeah. Actually, it started to study watermelons. That's was the first paper, yes.
Really?
By Fisher and Tippett. Yeah, actually, it was watermelon.
Fisher and Tippett for watermelon or water beds?
Yeah, for the no. It was really watermelons for the maximum size, something like that. I remember.
Really?
Yes.
Okay, that's interesting.
And then, okay, yes, obviously in the Netherlands, it became fundamental for the Delta project. So for hydrology and for the construction of dams and dikes and all the protections that are very famous in the Netherlands, because the Netherlands are under the sea level, so on average.
So let me make a few points, and then you can continue and make your points. Is it okay? I have a blackboard here that helped me install when you visited me in my Atlanta place years ago. And okay, yeah, exactly. So thanks for setting up, help me set up the board. And let's okay. So let's discuss what is at stake here. Number one, when you have very fat-tailed variables, you don't need a lot of observation because the tails carry a much stronger weight. So we believe our result is very robust, but nevertheless, we can test by scrambling things, and we had to deal with two problems. The first problem is reliability. So what we do is, given that there's traditionally we have really unreliable variables coming from historical data, we take a high and low of the observation, and then produce different time series somewhere in between the high and low. We apply that to wars because we know that historians are liars, but it doesn't matter, it washes out. And somehow we produce so many. I mean, we produce this time 10,000 series, but you can produce 100,000 series in between the high and low, and see how the parameters we're looking for, how do they fare? And effectively, our parameters don't change much with this. And then the other thing, of course, is we remove observation, which is another similar approach, but not as robust. We remove observation doing the jackknife, and we also did something called bootstrap, and we got pretty much no difference in the result. The result is the alpha that we're observing, and of course look up alpha. The alpha for a power law is a tail exponent of a power law. Is conventionally expressed as something like probability of exceeding x is going to be equal to something times x to the minus alpha. That alpha that we have here is below 1. No matter how we look at it, it's below 1. So that's the first result. Second point, we figured out the technique you and I, in doing the following. We like to use extreme value theory, which is very technical for this conversation. But then again, it started with the Delta project, as you say. Now I'm discovering it started with watermelons. And what we have here is a variable, which is how many people can die from a pandemic between 0 and an upper bound, okay? Let's say H, the upper bound.
Yeah.
So, or here we use L because we're only concerned with things that kill 1,000, L and H. You cannot technically work with a random variable that is bounded because we're looking at things that are unbounded. So we did a phi transformation, phi of X, say X is a random variable, okay? Phi transformation, and we did apply our techniques to the phi transformation, and we did an inverse transformation, phi minus 1, okay, of Y, an inverse transformation to get the parameter. It's a little technical, it's explained in the paper. It's also explained very well, I think, in our other papers on operational risk where we use the same technique. So these two approaches, one is how do you deal with liars, because historians are liars. The second one, and how you perform these transformation to be able to use extreme value theory, I think, okay, are new in the literature, and we have published 3 or 4 papers on around these. No?
Yeah. Operational risk, wars, and now pandemics. Yes.
And another paper on its own explaining the mathematics of these transformation and how you can extract moments. I remember from a conversation with the great, super great Benoit Mandelbrot, rest in peace. We said, it was a very interesting conversation, and we were puzzled. We said, if something has infinite mean, but it's bounded at H, wouldn't you think the mean would be H? That was my question. And Mandelbrot thought about it. He said, of course, it's got to be H. So I went for years thinking that if it's infinite mean but bounded, that the mean would be the maximum observation. Okay, not, of course. It turns out that not to be there, but to be somewhere in between. And so in our paper, we pulled that thing. Okay. One more thing I have to say about the results of the paper, because again, we're not explaining that all these approaches using point estimates, where you have a probability distribution and you're trying to summarize a probability distribution with 1 point. Okay, this is a probability distribution. And we don't know a lot about the probability distribution here, by the way, which is what matters. And you try to summarize it with 1 forecast. It doesn't work because a large number. There's this something called super forecasters by Petlock. Let's complete the S, okay? And of course, they try to gauge people on how good they are at forecasting these irrelevant variables. Avoid, okay? You may use forecasting, single point forecast for some I don't know which application. Okay, I really don't know which application.
When you know,
there are hardly any.
So when you know that something is, for example, inherently Gaussian or normal, then
no. Even with a Gaussian, it doesn't really work. I mean, we know from trading that binary options were banned in many countries because it's gambling. So the whole idea is we are not in there to estimate the point. Someone say, "Oh, what do you think will happen?" That is the realm of the charlatan. What do you think will happen here is to describe the statistical properties. And no policy should ever be made off of a single variable, which is actually the way traditionally we worked before these idiotic psychologists came in and contaminated the industry, okay, with their point estimates.
In finance is exactly the point of having all regulation just based on the value risk. It's
exactly. So yeah.
So that's exactly the point. Yes.
Okay.
So I think, I mean, so what we can take out of our paper is that we have for sure. So there is no discussion that our data set is not complete. For sure, it will be not complete because it's almost impossible to have all information about pandemics in the 2nd century or in the 3rd century, obviously. But Nevertheless, we believe that our results are robust because we focus on the tail. And when you are dealing with something that can generate a lot of victims or casualties, for example, in wars, then what really matters in terms of risk is are the maxima, are the upper order statistics, not just the mean or the bulk of the distribution. And the techniques that we have used, which is this combination of EVT, extreme value theory, and our transformation, is the idea that we try to get as much information from the data themselves, but at the same time, without being fooled, as you usually say, by the data themselves. So the fact that obviously the data contain part of information because we start from the data. So, but the fact is that instead of being fully parametric or fully non-parametric, we have this semi-parametric approach in which at a certain point, for what we cannot completely say about the tail, we are able to use an extreme value theory on the transformation of the variables, not to be, again, fooled by what, for example, you were discussing with Mandelbrot. We can say a lot of things. So we can say that the risk of observing a lot of casualties, even in COVID, we hope not, but it's not something that you can underestimate. So it's not something that you can say is just a flu, because that would be quite dangerous.
So two comments, one technical and one policy comment. Technical comment that we need to make is that the fatter tail the distribution, particularly if it's one tail, not two tail, the fatter tail, the less information you have in the body. Mm-hmm. So in other words, even statistically, you can have 1 trillion pieces of data here, no impact. One here dominates. Okay, so the statistical properties as the distribution becomes fat tail, move towards the tail.
Yes, indeed.
That is what is central, and this is something that people in finance are starting to discover after lockdown. That's the first comment about the methodology, which is why we can say incomplete information in the tail. We can remove half the information, nothing will change.
Yeah.
Say, okay, this is the interesting thing. You can dump 10 times the observation, and I don't think anything will change. The interesting thing about war is no matter what you do, no matter what you remove, where we had a lot of observation in war, even taking into account the fact that historians are liars, they either exaggerate or misrepresent, even nothing changed.
That's the beauty of that tail. When you speak about very large events, for sure, the observation can be, can be volatile because of the different reports and the different, so in the case of wars, it very much depends on who was the winner of the war, obviously.
Exactly, yes.
But at the same point, if it's a large event, then it's much more probable that has been recorded. So you can lose, for example, very small events because nobody will maybe record a very small fight in which 10 people died 100 of years ago. But if something big happened, there is a good chance that that has been recorded. So that's why also the maxima are so informative, because they are there. It's very unlikely that an event like World War II is not recorded, or an event like the Spanish flu is not recorded.
Yeah, and also there could be an underestimation. There might have been some pandemics that we didn't know about. Okay, it doesn't matter because we're able to handle that. Okay, so and the second point I will make is that, and that's the policy one, unless you have zero uncertainty about the disease. Mm-hmm. I mean, by zero, I mean really zero. Okay, 0, 0, 0, right? Uncertainty about the disease, you have to assume this distribution. And let us explain. We still don't know how many people this will kill, what will happen to the morbidities of of COVID, and of course, we don't know the mutation of that. Yeah. And worse, we live in a world that's too connected today, so we expect the tails, to remain fat. It's possible to reduce them. So it is imperative to kill the thing in the egg.
Yes.
Had people started using the drastic measures that we proposed in January, I mean, 4 months ago, we wouldn't be talking about this now. And you and I would have a paper in Nature Physics because nobody was scared about it. So the idea of the idea of killing something in the egg when it's too cheap is imperative. And when we look at history, I know Pasquale, you're a history buff, and of course we collaborate because we like history of wars. But when you look at history, you have nothing but quarantines. Why? Because the minute they suspected, say in Genoa, they suspected that one sailor was affected by disease, they took no risk. Sometimes they rejected the ship. They would tell, we'll go to France. France may take your garbage, not us. And they would shut down the town. So the idea of early reaction was imprinted in the history of the Mediterranean. Because they had a lot of commerce coming from Asia and they were really familiar with these classes of risks.
Yeah, one thing that I like, so one sentence that came out in our paper when we were writing it that I like a lot is the one where we say that actually, let's say the fact that people tend to be cautious and someone says paranoid about certain type of events, like for example, a possible pandemic, because people were scared and were afraid of the COVID even before it was defined and it was called a pandemic. So when it was still a contagious disease and not a pandemic. Now, the fact is that what I find annoying, at least for me, is that typically those that say that something is paranoid, something is exaggerated, are those that underestimate things. So obviously, if you have a model in which nothing bad can happen, then all reaction will appear paranoid to you. But then most of the times, those models are wrong.
Yeah, no, that's my war against what I call the IYI and skin in the game by saying all these people, they treat you as, you know, as if you were like a patient who has paranoia, when in fact you just have a normal reaction. It's that they're using the wrong probability distribution. If you use the right probability distribution, it's no longer irrational, it's no longer paranoia.
Sorry.
And furthermore, there's another element here that you know, we have discussed, a lot of people have discussed, I've discussed publicly. Never compare something with these properties to heart attacks.
Yes, indeed.
Because if your neighbor has a heart attack, odds are you won't have a heart attack. But if your neighbor gets COVID, odds are, you know, you're gonna get COVID.
Yeah, it's like so, when you fall from a stair. So I mean, when you fall from a ladder, yeah, there is the chance that if someone is close to you, you grab it and then he falls with he or she falls with you. But it's one people, two people, so it's not a contagious event.
Exactly. This is the mistake of Ioannidis, by the way, when he said, "Oh, at the beginning, you know, when people were not paranoid enough about it. Now people may be too paranoid." He said you have the risk of drowning in a swimming pool is higher for an older person, or I think he used a different one. He said that the car accident, the probability of having a car accident is higher for, you know, the deaths from car accidents. So, but when you look at it properly, you realize that for one person, maybe it was not true, but by the way, but assuming it was true, but for 1,000 people, if I tell you 1,000 people died today, odds are in that community, odds are it's more likely to be COVID than a car accident. Yeah. So they don't understand the scaling, that things scale differently for a power law than it does for other things.
Yeah, indeed, so, man. And it's very, unfortunately, especially in the media, this type of fallacy, so this size fallacy in which they compare things that cannot be compared, like heart attacks and a pandemic. They are unfortunately very common, and it's
yes,
a problem.
That's the problem of studying statistics. Statisticians make that mistake very often because they don't know, they know within a certain class of distribution how things work, like the Gaussian. The most cited statistician in the world, this fellow, the English fellow who does medical statistics, doesn't know fat tails. So he makes these mistakes throughout his I would see him on Twitter, and I, of course, muted him on Twitter. But I see these fallacies made even by the Royal Society of Statistics in the UK. They had a journalist editor, and it starts talking about irrationality of worrying about Ebola or something like that. They don't understand. You should not, and that's orthodox statistics, compare two variables in two different distribution classes. The problem is that the teaching of statistics is not mathematical. It's just like learning how to cook. So they are not aware of other classes of distribution. You need to deal with probabilists. And which is what I mean, you need to teach people probability for years before you let them do statistics, because then they can harm themselves.
Now, what I can tell you by my own experience is that when I was a student, and we are not speaking about 2 centuries, so it's a few years ago.
Yeah, okay, you're so young.
No longer, but okay, I'm not in my 80s. So when I was a student, and we're speaking, when I was a PhD student, so it's something like a little bit more than 10 years ago. So unfortunately, and that was very surprising to me, so extreme value theory was a sort of, I don't know how to call it. So if you were attending the conferences like the Extreme Value Analysis Conference that we organize every 2 years, then obviously everyone there was aware of all the results, because that was a closed community. But then as soon as you were out of this extreme value community, so this community of extremists, then it was like fundamental results like the Fisher-Tippett were not known, or even if they were known, they were not considered important. Like, okay.
Yeah, that's it. It's only insurance picked it up. Insurance companies picked it up.
Because
insurance companies know about it. Reinsurance, not insurance, reinsurance, because they need it. So basically, the teaching of statistics is crazily narrow. But you take finance. Okay, people don't quite understand that finance has the same problem, particularly if you have derivatives off of some product that's power law distributed, like anything that's off the S&P 500, like performance of a portfolio, or anything that has derivatives. In finance, they don't just quite understand the law of large numbers. It doesn't work there anymore the way they think it works.
Yeah.
So one day you and I, and we're telling the public here, you and I are going to do both a video and probably followed by a short book on statistics from a probability standpoint. So you go from something abstract, like the way I've done it at Rory. It's so easy for people to understand statistics if you start by explaining to them the law of large numbers. And they can very quickly see that it doesn't apply unconditionally. It applies only in some situation, because all of it is the law of large numbers, you see, everything. And the law of large numbers is only easy if you become asymptotically Gaussian, okay? And pre-asymptotically Gaussian. Now, things are not asymptotically Gaussian, always. And those that are asymptotically Gaussian, and this is the topic of my new thing, of my textbook, the Technical Concerto, Volume 1, that we'll say pre-asymptotics, okay? That's the central thing, is pre-asymptotically, you're not Gaussian, statistics don't work. So we have to teach people to think and reason and understand these. And hopefully you and I will do something like this, okay, to teach people who are afraid of the math, statistics. We tell them, forget everything you know. People think in terms of mean, variance, all these constructs, okay, come later. First of all, you gotta understand the law of large numbers. What is the probability distribution? How does it work? What are you looking for? Okay, and from there on, okay, start looking at statistical tools if they work. And most time for social science, variables like prices in financial markets, income, pandemics, it's not social science, but a lot of aggregate variables are not Gaussian. So, and they will never be Gaussian, okay, even asymptotically. So that's going to be the discussion.
No, I agree, because I mean, if you start from objects that are very well known and that have a lot of nice properties. I mean, if you take a random variable that is normally distributed, we know a lot of things about that. If you take a random variable that is exponentially distributed, we know a lot of things about that. And they are nice fields of application. I'm not saying so. They are extremely useful. So you have to know them. But then as soon as you introduce a very basic transformation, like taking something to the exponential, so if you take the exponential of a normally distributed random variable, then you get log normal, which is a tricky beast. If you do that with the exponential, you get the Pareto,
that's something very interesting. Something very interesting here. So now we're being dragged into more mathematics. But let's do this and then hop off because it's getting okay. So we didn't put in a paper. But let's say x t is equal x0 e r, you know, for that period, and t is time, okay? And then of course r is an average rate. R is going to be an integral rs ds over that period, t0 and t. So it's going to here t minus t0, xt0 xt, and 1 over, of course, t minus t0. Okay, so this is going to be r. Okay, now we discovered that xt is Pareto distributed, has Pareto tail. Okay, it means necessarily that r is exponential. So you can have an exponential has all the moments. So you can have the gross r exponential. The gross r is exponential, but what is shocking? Okay, it will have a mean, it will have a variance, it will be nice, tractable. Xt that comes from it will not be because we're exponentiating. Okay,
yeah,
so,
exactly, yeah.
So the interesting thing is a small little error you make in the estimation of r.
Yeah, it's enormous in there.
Okay, it explodes in t on the port. Okay, so this is where this is an interesting thing. So to conclude, I mean, we don't want to stay long. Please, Pasquale, do not edit this video.
Okay, no, I will not.
Because, and including this conversation, let's not edit. Let's make it normal. This is like Rory. We do it at Rory. Okay.
Yeah, sure.
This is, we're not salespeople.
I'm just cutting the first 10 seconds in which I say now I start the recording. Okay, that's
okay. All right, that's fine. We agreed on that. Okay, tutto bene. So I have to go to lunch. So
I have to cook dinner. So in any case.
Okay, lucky. I'd rather eat your food than my food.
Okay, hopefully soon.
Okay, great.
Okay, so thank you,
Okay,
Nassim.
arrivederci. Thanks a lot, Pasquale, for this wonderful conversation.